everyone. Hope everyone is having a good day today and is ready to work on some more confidence intervals. So last time we learned what confidence intervals were, and then we looked at confidence intervals for the mean, and we looked at a large sample. Now the biggest thing about that large sample was that we could assume everything was normal. So that kind of followed along with the whole chapter before on the normal distribution. So that first section of confidence intervals, everything works smoothly. So now though, we're gonna do confidence intervals for the mean with a small sample. So the question is, what if you go to do a problem and your data isn't normal, but you don't have a large enough sample? So we say what if, I don't think that pen is bright enough, hold on, we're gonna have rainbow day today apparently. Data isn't normal, but the sample not snakes, is less than 30. So if we're in this situation, what if the data isn't normal, but the sample is less than 30? We can't assume normal, we can't use the central limit theorem. But what I want you to think back to is, remember when we did the central limit theorem here on the board, and I used that really itty bitty example, and we took that graph that was not normal, and then we did some work on it, and we made that little normal bump in the middle. Remember doing that? That sample size was a sample size 2. And sure, the graph that we came up with wasn't normal. It wasn't a perfect bell-shaped curve, but it had the characteristics, didn't it? So even with a sample size of size 2, we were still able to get a little bump in the middle. So when your sample size is less than 30, the graph that you're getting is what we kind of say somewhat normal or sort of normal. So that's what we want to focus on, is that we say, we can say the data is sort of normal. Now, just because we say something is sort of normal does not mean we get to use z-scores, okay? The normal distribution, the normal curve is very, very special. And if it doesn't fall into that characteristic of being normal, having that perfect, nice bell-shaped curve, we don't get to use z-scores. We don't get to use easy peasy, big Z. We don't get to use any of our z-score formulas. But what we can use is a different distribution called the t-distribution. So we use the t-distribution. And just to get in the habit, it's a lowercase t, okay? So I don't know that it really matters, but the t-distribution is a lowercase t. And the t-distribution, or distributions, this is a family of graphs that are all approximately normal. So just as an example, remember, this means that we're looking at sample sizes that are less than 30, but we can still get these kind of approximately normal graphs. So approximately normal means it might be something that looks like this. Sure, we got that nice bump in the middle, but it's not a perfect bell-shaped curve, is it? Okay, so that might be one example. Another example might be one that's very shallow, but it still has the look to it. Okay, it's just a big wide bell, but it's not a perfect normal curve, but it's approximately normal. It has the right idea. Or another common one would be if we go to graph And we've seen this a bunch. We see something like that, right? So we end up with a tail on one side. If you step back, it doesn't look bad, but is it perfect? Is it really symmetrical? You know, this tail is going out a little ways. I don't know, okay? So these are examples of graphs that would fit into the t distribution, which are the guys that are approximately normal. Okay, so and the key is that these guys depend on sample size. Okay, so these depend on sample size. So what our sample is, because it's going to be less than 30, but what it actually is actually tells us how normal the graph is or how not normal the graph is, okay? So we need to take into account sample size when we are thinking about t distribution. Okay, so what we're going to look at here is something that we call degrees of freedom. And degrees of freedom is an easy little thing, you just kind of have to remember it. Normally it's just labeled DF. And degrees of freedom is found by taking n minus 1. So when we say that these graphs depend on sample size, they do. But actually when we do these problems, we are not actually going to use the sample size. We're going to use the degrees of freedom, which is just taking our sample size and subtracting 1. Okay, so get that in the old brain that degrees of freedom is 1, or is n minus 1, not 1. Boom. Degrees of freedom is n minus 1. Okay, so now what we need to do is learn how to find t-scores. Finding t-scores. So in the last section, or in the last chapter, we did a lot of finding z-scores. And on your calculator, you had that inverse norm, and that helped us find t-scores, but that's not gonna work for us here because we're not normal. But guess what your calculator does have? Instead of using an inverse norm, this time we're gonna use, I don't know what's wrong with me today, it does not start with n. We're gonna use inverse t, okay, inverse t. And I'll show you where it is, but it's just right next to the inverse norm, which means you have to think about it a little, make sure you go to the right one. And when we do inverse norm, it's gonna ask us for the area, for the comma, and then it's gonna ask us for the degrees of freedom. So those are the two things that we need to plug in, or sorry, when we use this inverse t, not inverse norm, inverse t. So inverse t, we put area and then degrees of freedom. So let's do a little example here so we can figure out how this is going to work on the calculator. Let's see. So let's say that we want 95% confidence and we know that n is equal to 21. Okay, so we're doing some problem, and in it says find a 95% confidence interval, and oh no, the n is only 21. So this is not a z-score problem. This is going to fall into our t-score, or our t-distribution problems. So we're going to start the problem the same way by making a little graph, and now I know I made a really nice normal graph, but remember this is just somewhat normal, but the graph is just a visual for you. Now remember that this 95 is this whole area, 0.95, but we just want half of it. So we take the 0.95 and divide it by 2, which will get this as a 0.475. And again, we don't want that guy, we want the area of the tail. So the area of the tail out here, if you go 0.5 minus that would be 0.025. Okay, so remember it's a little bit of a process to get there. So divide in half and then find the complement. Divide in half and find the complement. But now we're ready to do this inverse t part of it, and we're going to find a t-score. This is not a z-score, we're definitely doing a t-score here. So we're going to go inverse t, and we're going to get 0.025 in there. And then it asks us for the degree of freedom. Well, if our n is 21, our degree of freedom is 20. Okay. All right, now for some of you, your calculator is going to do it just like this. You're going to put in inverse t, it's going to get in a parenthesis, you put in 0.025, comma, 20. I don't even think you need to close the parentheses, but just hit enter. Now, for others of us, if our calculator is a little bit more fancy schmancy, it's going to look a little different. So let's go ahead and look at that real quick. Okay, so if you're doing this, you're going to the same place where everything else with the normal curve was. So second distribution, and then there's our normal CDF, our inverse norm, and lo and behold, right underneath it is inverse t. So we click inverse t. Now, in our case with this calculator, it asks us for the area and the degree of freedom. So I put 0.025, here's my arrow. Degree of freedom is 20, arrow, paste. Now see how it pasted in there for us? So inverse t, 0.025, comma 20, okay, and then hit enter. And we get -2 point blah, 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 blah. I'll go ahead and write that on the board, okay? Now, the thing is, remember that negative just means that we're on this side of the graph, but when we're doing this, we don't need the negative or the positive side, we just need the number. So we can say that our number that popped out without the negative sign, we don't need it, is 2.08, and then I'm going to hit with this with a 6 at the end. 2.086. Okay, and here's the thing about this. If this was a z-score, we would have rounded this to 2.09. This is a t-score, so our t equals 2.086, and this is always going to be in 3 decimals. So t-scores have 3 decimals, while z-scores have 2 decimals. And that is, again, to help us keep things straight in our brains. Z2, T3. Now, again, remember, when you put this in here, there's a negative sign, which actually there's 2. There's a plus or a minus. There's this guy, which would be the minus, and there's this guy, which would be the plus. Okay, but we don't really care about the sign. It's just the number that we're trying to find. The boundary number there. What's the number on each side? But since it's symmetrical or somewhat symmetrical, we don't need the plus or minus sign. Okay. All right, so let's do another one of these just to make sure that you got it in your head as to how to do this. And then we'll get into an example here. Okay, so this time let's say that we wanted 94% confidence, and n was equal to, let's just go with 7, okay? 94% confidence with an n equal to 7. So this sample size is quite a bit smaller, quite a bit smaller. Okay, so again, our graph, somewhat normal, who knows what it looks like, okay? But the idea is that 94% confidence is gonna split over the middle. So we only want 1/2 of it though, we only want this side. So we're gonna go 0.94 divided by 2. Okay, so 0.94 divided by 2, let's see what's that gonna give us. A 0.47. And if that's 0.47, it means that this bit out here is going to be 0.03. Okay, so remember, it's always, oops, there goes my pen. It's always that tail that we want. So we're going to go inverse t, and we want an area of 0.03, and we want a degree of freedom of 6. Okay. 0.03, comma 6. Okay, so we'll go ahead and do this one. Practice it again on your calculator. Okay. So inverse t. Boop, boop. Inverse t. 0.036. 0.036, and let's see what pops up. Negative 2.313. Remember, we don't need the negative sign, so 2.313. All right. Remember, 3 decimal places there. So 2.313. So that is our t. T equals 2.313. All right. Turn that off for a while. Okay, so we are learning how to find t-scores. So instead of inverse norm, you're using inverse t. Now, let's go ahead and get going on the confidence intervals. So we're going to do the whole thing now. So here's the formula. So confidence intervals, CI, for mean small sample formula. Now it's going to look very similar to the last one. It's just that we're going to have a couple little changes here. So this one starts with x bar minus t sub alpha over 2. So because we're not dealing with a z-score, it's a t-score. That changes that out. Times s over the square root of n is less than mu, which is less than x bar plus t sub alpha over 2 times s over the square root of n. All right. So as I said, similar, not exact, but similar to what we saw last time. So the t is replacing the z on both sides. There's the plus and the minus. That's why we don't need it when we find it from the calculator, because it's in the formula. The only other difference is that in the large sample one, we have a sigma here, and in this one we have the s. So in both cases, it means standard deviation. But a lot of times the assumption is when you're doing one of these small sample problems is that you only have the sample standard deviation. The sample standard deviation. Here's the deal. If we were all going to be statisticians, we would really nitpick on that and decide, do we have the sample standard deviation or the population standard deviation? What standard deviation are we working with? But for most of us, it really doesn't matter. And I know that others, statistics teachers are like, what the heck are you saying? But for the everyday person, it really doesn't matter. So don't worry that that's S as opposed to sigma. Just whatever standard deviation they give you, stick it there, okay? What's important to us is that we're dealing with a small sample here, and that's what's important. Okay. All right, so there's the formula. We actually know how to use these formulas, so we're ready to see our next example here. So let's see what we got here. So this says, find a 90% confidence interval for the true mean cost of a graphing calculator if a sample of 12 has a mean cost of $87.12 with a standard deviation of $4.86. All right, so if you look back at what we did last time and then you look at this one, the problem looks almost exactly the same. Almost exactly the same. So you have to be very careful now. So when you read the question, reading the question and really paying attention to what's in there falls on you. So as we look at this guy, what I want you to see is that as we come down to the sample size, our sample is just 12. So because our sample is 12, that means that we are not normal. So it means that instead of using z-scores, we have to use t-scores. So that's what we're looking for, that tells us that we're now using our new t-score formula. Okay, so that's it though, that's it. So is it very important that every time you read the question, you pay attention to the sample size? Most definitely, absolutely most definitely. Okay, so what we need to do then first is to find our t sub alpha over 2. So over here we'll say find t sub alpha over 2. And now remember, this is going to be completely different. You know, if we were doing a z-score, it would be 1.65 and we would move on. This one's going to be completely different because the size of the sample, everything comes into play. So if we've got a 90% confidence and we divide that by 2, that puts us at 0.45, right, or 45%, which means the complement is 0.05. Now basically, we just did 2 examples of this where we drew the graph and we showed each step. I'm just basically doing that now, but without showing the graph. So if you need to draw the graph and do it like we did the last 2 examples, go for it. If not, you can think it out, draw the graph, cut it in half, do the whole thing. But we come up with a complement of 0.05. So we need to find inverse t. We're going to use 0.05, and then our degree of freedom is going to be 11, right? Okay, so give this a go, and let's see what pops out of the calculator this time. Second distribution, inverse t, 0.05, 11. And I got negative 1.796. How does that look to everybody? Now remember, that's going to be our t sub alpha over 2. Negative 1 point, or just remember, we don't need the negative, so just 1.796. So remember, it's tempting to write down the negative because that's what the calculator spit out, but you can just put the number. We don't care about the negative because it's falling right there. Okay, now we're ready to start. So we need our x bar, which was our mean cost of our calculators. So 87.12 minus our t-score, 1.796, times our standard deviation, which was 4.86, over the square root of n, which would be the square root of 12. Now notice here, we used 11 up here, but we're back to using 12. So 11 only comes up in the inverse t, okay? 12 back here. And then hopefully the mean is in the middle. And just like before, the upper side is just the same thing, but with a plus sign. Okay, so not much different on the upper side. Now think about this. When we did this before, I asked you to find this part first. Okay, do you remember what that part is called? Okay, hopefully you remember it was the margin of error. So remember, this is the 2-step process. So just like before, we're going to find that part first, and then we're going to add, and then we're going to subtract. Okay, so we have 87.12 minus. Okay, so again, calculator out. 1.796 times 4.86 divided by the square root of 12. And I got 2.520, let's say. Okay, if you do your rounding appropriately. So on this side then it will be 87.12 plus 2.520. Oh, I guess I need my calculator again. Okay, so we found the margin of error. Now we'll go ahead and subtract. So 87.12 minus 220. So I got 84.60 on this end. And $89.64 on this end. Look good. Now, as we all know from last section, that doesn't cut it. I have, yes, seen your 2 steps, fantastic, 2-step process, but never, ever, ever are we going to leave a confidence interval in that form. We are going to write our sentence. So we say we are, how confident were we? 90% confident. The true mean cost of graphing calculators is between $84.60 and $89.64. Okay, so we are 90% confident that the mean cost of graphing calculators is between $84.60 and $89.64. So the idea here is, like, how would we use this? Well, if you were going to go buy a graphing calculator, which some of you did, but a lot of you rented yours or borrowed it, okay, this would help you out. If you saw this, if someone had done this study and they come back and they say, you know, there's 90% confidence, I'm 90% sure that you're gonna have to pay between 84 and 89 whatever dollars for your calculator, all of a sudden that gives you a real idea. If you go, oh geez, wow, that's kind of a pricey situation. And think about this. Let's say that you did buy a graphing calculator and you spent $95. Did you fall in the interval? You didn't, did you? So now, we were only 90% confident, so there's a 10% chance that it's gonna fall outside the interval, but still, if you paid like 100 or something and you fell outside this interval, you might be going, crap, I think I overspent, okay? So that's the idea of how this helps us out. It helps people pinpoint within a range, not exactly, but within a range, okay, what am I gonna, in this case, what am I gonna have to spend? All right, now, one thing that we want to discuss before we go any further is rounding. And the reason why I say that is because I just said, let's say your calculator is between $84 and $89. And then I corrected myself and I said, oh, I mean about $89. Because if I wrote $89, I just rounded this interval and I didn't round it very well, did I? Okay? So we need to talk about rounding when it comes to an interval. This confidence interval gives us 90% confidence. If we were to round this interval and round it and make it a little smaller, so if we were round in on the ends and make it smaller, we lose our confidence. We cannot be 90% confident if we round in. If you round out and make the interval bigger, we can maintain our confidence. So let's say it like this. I can be 99% confident that we're going to finish this lecture in between 10 and 170 minutes. I can be 99% confident that this lecture is not going to go longer than 10 and 179 minutes. Well, that interval is really dumb, right? Who wants to be sitting here for another 179 minutes? Okay, but that interval is huge, and because that interval is huge, I can be very confident because I know that I'm going to finish in that time limit, okay? As the interval becomes smaller, I have to be less confident. So if I said we're going to finish this lecture in the next 10 to 20 minutes, I might only be able to put a 90% confidence on that because as you've seen in the past, dogs have come running through here, birds have flown out, kids come in and bother me. So it's very possible that we have to take a break because something happens and I have to take a break and go take care of that and then come back. So I can't be sure that we will finish within 10 to 20 minutes. I can't. I could say 90% because I know many more examples we have and blah, blah, blah. But I can't be like 99% sure. So the idea again there is round, when you're rounding confidence intervals, round always to make them bigger. Never round them smaller, always bigger. Or the key thing is just don't round. Leave the numbers the way they were and be done with it. Okay? So let's make a note of that though, so we have our rounding rule. Okay? What I'm looking for here. Okay, so basically written out here is what we just said. If you make the interval smaller, we can no longer maintain confidence, which is bad. You do not want to say you're 90% confident when you're not. Okay? So then again, the rule is always round to make the interval wider or larger, however you want to say it. So if you are going to round, you round down on the low end and you round up on the high end. You stretch your interval out, you never bring it in. Always out, never in. All right, so, okay, I thought there were too many pages here, there are. Okay, one more example here. So this time, let's go back to our blue pen. Let's see, we have find a 99% confidence interval for the true mean time spent Easter egg hunting if a sample of 18 families spend a mean 47.3 minutes with a standard deviation of 5.91. All right, good. So remember, the first thing we do is we read the problem. Now, every time we read the problem, we are focusing on the sample size, And because that is 18, that means that we are using T and not a Z, right? So we're looking for a T sub alpha over 2. Okay, so take a minute or two with our 99% confidence and our degree of freedom, which is 17, do the process again and see if you can come up with a T-score, okay? So the 99% confidence and a degree of freedom of 17. And if you plug that into your calculator, right, find the half of that and then find the complement and do the whole thing, you should get a T sub alpha over 2 of 2.898. So work that out. Use your inverse t. Make sure that you can do that on your own. And then we will stick it in. Okay, so otherwise we've got everything we need. Now I know I erased the formula, but you should have the formula. So you start with the mean. So we start with the 47.3. We subtract our t-score, so 2.898, times our standard deviation of 5.91 over the square root of, not degree of freedom, but of our sample, which was 18. Again, hopefully the mean is in there, plus, now I seem to have run myself out of space, but the nice thing is that's just a repeat of this side, so even though you can't see it because I ran myself out of space, we don't really need it, right? So, margin of error first. Let's calculate that little guy. 5.9. So we still have our 47.3, and now I have a minus 4.04. That sounds good to everybody. That's what I got. And on the upper end, we have the 47.3, but it's just going to be plus 4.04. Okay, so there's our middle step. Now we'll subtract. Which gives me 43.26. And if we add, gives us 51.34. Okay. Now here is a perfect example of what I'm talking about with the rounding. Again, easier just to leave it as decimals, okay? Just leave the decimal there. There's nothing wrong with that. But if you were talking to someone, do we normally tell people decimals of minutes? Do you tell someone, I hunted for Easter eggs for 43.26 minutes? No. Normally we would just round, okay? But in this case, this would round to 43. If we were rounding, this would round to 43, and that's fine. But up here, this would round to 51. That is not fine because the actual interval endpoint is 51.34. So by rounding off that 0.34, if you just wrote it as 51, by rounding that off, you are pulling in your interval just a little bit, but just enough that we lose our 99% confidence, okay? So if, again, I wouldn't round. If it was me, just don't round. But if you had, for some reason, you were like, no, I must round. Okay, this guy would go down, so it would go to 43. This guy would go up, though. So it would go to 52. Even though that's not the way the rounding says, the only way to round is down on this end and up on this end. Okay? Make the interval wider, not shorter, not smaller. Or, as I said, just don't do this. Boop, boop. Keep it with the decimal. So we go ahead and write our sentence. We say we are 99% confident the true mean egg hunting time is between 43.26 and 51.34 minutes. Now again, I want to be clear, this is, I didn't go around investigating how long people hunt Easter eggs. This was just totally made up because last week was Easter, okay? So don't be going and quoting this. But in my made up world, basically we can say that there's 99% confidence that the Easter egg hunting time is between 43.26 minutes and 51.34 minutes. So if I, as another separate family, allotted an hour of time for Easter egg hunting, would I be okay? Yeah, I'd be okay because the interval falls less than an hour. Okay, again, in my made-up world, okay? I just totally made those numbers up. But there we go. So the difference now is that t-score rather than the z-score. Otherwise, everything else is the same. So the process doesn't change, but the t rather than the z, which falls on you to be careful when you read the question. Okay, see? We finished between 10 and 20 minutes. Ta-da! Okay. All right, guys, I'll see you next time.